Good morning, ladies and gentlemen, and welcome to the Projects Day presentations for the Department of Physics and Nuclear Engineering. We have our first presenters here. I'm pleased to announce Cadet Ruabia, Cadet Porter, and Cadet Willis. Gentlemen, the floor is yours.
Thank you, sir. Good morning, everybody. My name is Cadet Ruabia. We'll be speaking about our project on determining minor planet periods through light curve analysis. So in short, we're measuring the rotational periods, so how long it takes to complete a full rotation, for asteroids in deep space, mostly beyond the orbit of Mars. So here's our agenda today. We'll begin by talking about some theory. We'll talk through how we select asteroids, then do our data acquisition and processing systems. We'll finish with research relevance, and we'll have time at the end for questions. So please don your 3D glasses and take a look at the screen. Now you'll notice that this asteroid here is asteroid Bennu in a photo taken by NASA. It's very irregular. There are a lot of bumps on it, a lot of different materials throughout it. Now for that reason, as this asteroid rotates, it will appear brighter or dimmer according to which stage in its rotation it's currently in. That irregular surface will create that differential across time of its brightness or its luminosity. So if we measure its brightness over time and we plot that on a graph, you'll see here in figure 1, we have a concept map of what that light curve will look like. Its brightness will decrease and increase over time as it's rotating. With that information, we can determine how quickly it rotates by measuring the time it takes for it to complete those rotations across that graph through the time between peaks. So essentially, the time between multiple peaks just gives us that rotational period for the asteroid. In order to select asteroids, the first criteria we use is we look for asteroids that have unknown rotational periods. Because of course, that's our contribution to the scientific community. That's what we're adding. Additionally, we need asteroids that have a favorable ephemeris, which just means it's in the sky at night for long enough that we can image it. Additionally, it must be bright enough. It needs to have an adequate luminosity in order for the telescope that we use to get images of it without the exposure times being too long. So for us, we usually want a 5 to 10 minute exposure because the asteroid will be moving while we're doing exposures, and any longer will make a blurry picture. We started with a validation attempt using Eleonora 354. That asteroid has a known rotational period. So the idea, and that's our data in figure 2, the idea there was to use our methods and validate a procedure with a known rotational period to see exactly what would go wrong if we did everything as planned. And actually, some things did go wrong. That is not perfect data, and we did not determine its correct rotational period with Eleonora. We then moved on to Cobstar 2427 and Donna Shirley 5649. Those two asteroids have unknown rotational periods, but they proved to be inadequate in either luminosity or ephemeris. So the data there was no good either. We're currently getting promising results from Dan Green 2068. That asteroid is bright enough and close enough to Earth that we can get good imagery, and we have some great data that we'll get to at the end of the presentation from that one. Right here is the data we get from NASA's JPL Small Body Database Query, and that's really just a table of all the data from different asteroids according to which one we choose. And you'll see that it gives us the ephemeris by hour or half-hour intervals, and it also gives us its apparent magnitude. We need an apparent magnitude to be always below 16. Lower is brighter in order for the telescope to pick up good enough images of those asteroids. And I'll turn it over to Cadet Willis.
Hey everyone, I am Cadet Willis, and I'm going to be taking over for the data acquisition portion of the project. It's basically using the West Point Observatory to actually get the photos of the asteroid. So, as Ramsey said, we need an asteroid that's bright enough that the telescope can pick up on. What we found is typically an apparent luminous magnitude of 12 is what we're looking for. For reference, Andromeda Galaxy has apparent luminous magnitude of 3. That's on a logarithmic scale, so Andromeda is approximately a terawatt brighter than the asteroids we're looking at. Now, because they're so dim, the objects that we're looking at, we need to have very long exposure times in order to actually pick up on them. Basically, the camera continuously looking at the asteroid without the asteroid moving in frame for a long period of time. We usually found that's between 5 and 8 minutes, depending on the night. Additionally, we need to pick up the asteroid for an entire rotational period. Most asteroids have a rotational period around 2 to 10 hours. That's the window that we're looking for, so we need to be able to get data on the asteroid for that period of time. So our mission criteria to meet all that is that we need to have precise imaging of asteroids for as long as 7 minutes to get individual images. And we have to do that continuously for around 5 to 10 hours. That's what we have to accomplish in order to get a proper light curve that we can publish. So I'm just going to go through the systems that we have inside the West Point Observatory, 5th floor Bartlett. First one, most obvious one, is the telescope itself. You can see the main optical tube at the top. Mounted to that below it is the mount, which actually slews the telescope and allows us to point it at wherever we want. At the rear of the telescope, we have a bunch of supporting equipment that allows us to focus and rotate the imagers, which compose of the auto-guiding imager and charge coupling device CCD imager, which is what's actually taking the photos. In addition to that, we have the dome as a separate system, which primary purpose is basically to block against weather and light pollution, which comprises of the dome slit and the actual dome itself and the motors running it. Finally, we have the remote sensors that are attached to the outside and some inside the dome. This allows us to operate the dome remotely, getting data on wind conditions and visibility, along with the status of the telescope itself on the interior. Connecting this all together, the dome and mount are talking to each other continuously, making sure the telescope is actually pointing out the slit so we can see the sky. The telescope and the dome are also connected to the SkyX software. That's what we use to actually program the telescope to take images for a period of time. And everything is connected to the remote network. This allows us to control the entire system remotely. Currently, we're doing that from the club room immediately below the observatory, but we hope next semester we can do so from the barracks rooms, extending the amount of time we can actually do imaging sessions because we don't have to worry about taps. So, quick imaging session concept. You see two pictures here. The one that's a little bit bigger is the main CCD chip, what's actually looking at the asteroid, combined with a smaller chip on your right, which is the auto-guiding chip. The idea is that we get the asteroid into the main chip and start the 6 to 10 minute exposure, followed by continual auto-guiding pictures taken from the smaller chip. The auto-guiding chip is focused on a background star and is continually taking 10-second photos, basically trying to keep that guide star that's inside the auto-guiding chip as still as possible. If it starts bouncing around, that's an indication that the pointing of the telescope's off, and we correct for that to make sure that everything's staying as still as possible in the main image. Our results from a 6-hour session is what we see here. I'm sure Colonel Baker can see the asteroid in the main image, but we zoomed it in for everyone else. This is the compilation of 6 hours of images, about 50 total. And you can see it just zooming across the sky from the right to the left in order to, the asteroid is right there. So this is all the images that we have from a single session. The idea is we want to replicate this over multiple nights though. I'm gonna pass this on for data processing.
Yeah, so at this point, we just have pretty pictures. Now we need to turn it into actual data. So what you're seeing right there on the left and on the right, these are the same image twice, and it's an image of Dan Green. But once we have the image, we have to get a match. That's the first step in processing the data. And what that means is the telescope will tell the software about where it's looking at in the sky, and then we also tell the software where the telescope is located on Earth. And from that, it gets a pretty good idea of where it's looking, but it has to match these background stars to its catalog of stars that it has in the software itself. So it matches, its brightness and their relative location to each other. And when it matches that, it's able to tell you exactly where the asteroid is, right? It's that tiny little yellow circle, if you can see it right there. And so once a match is made, then we pick comparison stars. And comparison stars are kind of the most important part of this. They filter out some of the confounding variables you get from the environment, stuff like light pollution, smog, cloud cover, that kind of stuff that affects our data is mitigated by what's called differential photometry. And it's not calculus, it's actually just the difference between what these catalog stars' brightnesses ought to be versus what they actually are in the image. And if it knows the difference, it's able to figure out the difference between what we're seeing in our asteroid and what it actually should be. The first comparison star, you usually do about 5. The first comparison star is the most important. It's the anchor star. And the purpose of the anchor star is to allow you to correct if anything goes wrong while you're taking pictures. So if the telescope moves a little bit, or if just something happens where it loses track, the software loses track of where that target asteroid is, you can click on the anchor star, tell it where the anchor star is, and then it figures out where everything else is based off of its relative position to that anchor star. And what you're seeing on the left here, that's a plot of all of the different background stars, all of these little black dots circled in red. And when you're trying to pick the comparison stars, it's important that you pick a star that's a constant brightness and the same color as our sun. Because asteroids don't emit their own light, they're just reflecting the sun's light, you want it to be about the same color as the sun, just because it makes it a better comparison star. So once you have all your comparison stars, once you've got a match, you can finally start to plot the data. And this is what you're seeing right here. This is what we plotted for Dan Green. And as you can see, it matches up with what we hope to get theoretically pretty well, right? Looks like a cosine wave. And the idea is just that this is the actual brightness of that asteroid versus time. And as you can see, just like we hope to, you can start to compare the peaks and decide, and figure out the rotational period of the asteroid from there. In the future, we would like to do more and more sessions so we can, further strengthen our position and augment this data with multiple days. But so far, the cloud cover has not quite been conducive to taking images, so we're hoping that this will improve in the future.
Thank you. So why is this important? Scientifically, this helps us build a body of data for each asteroid cataloged by NASA. That helps us learn more about those asteroids' properties when missions go and send spacecraft to those asteroids for science and for even commercial mining. Additionally, this is important for the Army. One of the Army's modernization priorities for air and missile defense is space domain awareness. Now, this is going to help us understand ways that we can optically track objects in deep space or even in Earth orbit. So that's important because passive tracking will allow us to conduct those missions without any emissions of photometric data or electromagnetic waves that could compromise the position of whomever is doing that mission. And thank you. That concludes our brief today. I believe we have time for questions, sir.
Yes.
Sir.
Could you go back to slide 5, please?
Yes, sir.
So on the validation attempt for Eleonora 351, did you find like what the problem was, or did you make an attempt to revalidate your procedures with that?
Yeah, so most of the problem for Eleonora came from we weren't picking constant star brightnesses for our comparison stars. So actually quite a few stars are variable in brightness. And so if they're changing, it's not good, right? Then we don't actually know what the brightness of the asteroid we're looking at is. So that was a problem. And then we also just got better at taking images with time. So it's just a couple of things. We just got a little bit better at our processes.
It was a lot of attention to detail. Like, for example, we got better at not standing around in the actual observatory while we're taking images because the telescope is extremely sensitive to vibrations, and even just standing near it and like moving this much as I'm doing right now, it's enough to throw it off a little bit and just mess with your data, mess with your image. So we just got better with our procedures, cleared up a lot of those little details, and as you can see, we got much better data once we did Dan Green.
All right. Thank you for sharing your research with us. Let's give them another round of applause. All right. So our next presenters are cadets Vincent, Gasperi, and Gonzalez. And whenever you're ready, please begin.
Good morning, ladies and gentlemen. Today we're going to be talking about the Soldier-Mounted Advanced Radiation Tracking Detector, also known as SMART.
Hi everybody, my name is Vincent Gasperi. I'm from Boca Raton, Florida. I'm a nuclear engineering major, and after my completion of basic officer leader course, I'll be heading to Italy for my first assignment.
Hi everyone, I'm Valentina Vincent. I'm from Newcastle, Pennsylvania, and after graduation, I'll be going to Fort Rucker, Alabama to learn how to fly helicopters.
Hello, I'm Enrique Gonzalez from Clarksville, Tennessee. I'll be going to Fort Campbell after PaNE.
Today we're going to be speaking to you about how an increasing need for advanced nuclear detection capability, along with an increasingly multipolar world and the concern for nuclear weapons, has necessitated a design that can enable soldiers to effectively track and locate nuclear material on the battlefield. Our project, fitting within this environment, is the SMART detector, a fast neutron portable soldier-mounted detector.
So one of the most prevalent threats to modern society right now is the possession of special nuclear material by either a non-state actor or a nuclear adversary. As you can see, there's two types of special nuclear material that we're focusing on: highly enriched uranium and weapons-grade plutonium. Weapons-grade plutonium poses the bigger threat because you can take the weapons-grade plutonium and put it in smaller and smaller packages but still have such devastating effects. And so the issue right now is to be able to detect these fast neutrons given off by the plutonium-240 without losing the information on energy, momentum, and direction.
In order to understand this problem, we have to understand nuclear detection generally. Basically, a radiation source emits alpha, beta, neutron, or gamma rays, and that's incident upon a detector volume. That detector volume produces a response. That response can be measured and outputted to a user in order to distinguish how many counts or incident particles, the waveforms that it's producing, or the energy that's involved. Those pieces of information can be used to decide what to do with the nuclear source or where it's coming from.
So how do we detect fast neutrons? Traditional methods include taking the incident fast neutron, thermalizing it or slowing it down in order to get information carriers, which then give us an output. However, in this process, we lose critical information such as energy, direction, and momentum data, which also makes it very, very difficult to do spectroscopy and localize. So our group has coined the term advanced radiation tracking, which is the art of SMART. And it takes the traditional method of fast neutron detection, and instead now we go from an incident fast neutron directly to an information carrier to get an output. And in doing so, we preserve the critical information such as energy, momentum, and directional data. The device that we use to do this is the time projection chamber. So the time projection chamber was not intended to be put on soldiers to detect special nuclear material. It was intended to be a high-energy physics experiment only in the laboratory. However, over time, the size of the time projection chamber has decreased, which allows us the opportunity to take this high-energy physics, make it portable, preserve direction, momentum, and energy information, and put it all into one package known as the SMART detector.
So what is a time projection chamber and how does it work? On the screen on the left side, you'll see a cross-section of a time projection chamber, which consists of a charge-coupled device camera at the top, an anode mesh at the bottom, and they're connected by an electric field cage in between. An incident fast neutron hits the target gas, in our case helium-4, producing a recoil nucleus that ionizes the gas that it's within. That ionization produces electrons that drift toward that anode mesh and create sparks at that high voltage mesh. Those sparks can be pictured by that charge-coupled device at the top and produce a track like on the right side of the screen. That track can give you the x and y direction of that fast neutron, and the z direction can be resolved by analyzing the amount of energy deposited on the track's graph.
So the biggest issue right now is to be able to take all the signal information processing, put it on the warfighter, and allow us to be rugged, lightweight, portable, and hopefully in the future airborne capable. So that's kind of what we're doing, is taking our big focus for the SMART detector is taking both of these together, putting it in assembly, giving it to the warfighter, and training them to use it.
How do we do that? How do we take a high-energy physics problem and put it into a soldier-mountable device? There are a couple of ways and a couple of things we need to accomplish. The first of which is minimize size and weight and maximize our active volume. We do this with a printed circuit board design that takes in the electric field cage necessity and turns it into something capable on the battlefield. Another thing that we had to create and design was the pressure vessel the entire thing is contained within. And maximizing the amount of active volume and creating a rugged and robust design will increase the warfighter's capability to locate special nuclear material. One of the most important pieces of our detector is the resolution that you get from the mesh at which the electrons are scintillated. That mesh has to be absolutely perfect with zero defects in order to produce good results. That process is another thing that we had to improve upon in order to enable the warfighter.
So the first step we took in optimizing the time projection chamber in order to make the smart detector was changing the old copper ring design. So the copper ring design in the time projection chamber, they were a centimeter in spacing, thus creating a centimeter of dead space within the detector volume. So instead we used a printed circuit board which has copper traces now instead of copper rings, and these copper traces are a millimeter in spacing, thus giving us a millimeter of dead space within the detector, which is less than the centimeter we had previously. So now we have more active volume within the detector, and the entire volume of the detector has gotten smaller, which allows it to be more portable. If you look at the top right, you can see a zoomed-in version of what the printed circuit board looks like. And so we had to solder resistors in between those millimeter spacings between the copper traces. And it's on a flexible material, which allows us to bend it in a cylinder and place it within the detector.
On this slide, you can see the impact of using a printed circuit board design. On the left side of the screen is the copper ring design and a simulation of the electric field within it. On the right side is a simulation of the electric field with the printed circuit board design. The color gradient within those two figures is the electric field strength in volts per centimeter. On the left side of the screen, with the copper ring design, there's a distortion and large gradient between the outside of the electric field at the corners of the copper rings and within the electric field itself. Moving to the printed circuit board will make our data more resolute while also decreasing size, weight, and increasing active volume. You can see there's much less distortion on the edges of the electric field and a far less severe color gradient within it.
Another focus for our optimization deals with the imaging of the actual particle tracks within the chamber. So on the left side of the screen, you can see the CCD camera assembly, which is made up of the camera lens itself, the image intensifier, and the CCD. So we use the image intensifier to allow us to still have high resolution within the particle track camera itself, while also using the camera lens to help decrease the focal length that we needed. And this allows us to decrease the size of the chamber itself by allowing us to take pictures closer and closer to the actual scintillation process itself. On the right side of the screen, you can see the aluminum chamber itself, which we took to vacuum to clear out the contaminants of it, and then we filled it with helium-4 as the target gas and used carbon tetrafluoride as the quenching gas.
One of the most vulnerable components for statistical resolution of the detector is the avalanche region of the uniform electric field. This region is built by our mesh. In order to create meshes without defects that would warp and bend under voltage, we had to create a process that ensured everything was continuous and could be repeatable in time. On the left side of the screen is a mesh stretcher we designed specifically for that purpose. Along with the process used to create those meshes, cut them, and stretch them, we've created a way to produce stretched, continuous, zero defect meshes that can be used within the detector and the electric field cage design shown on the right side of the screen.
So what is our current progress? So far we've gotten the detector down to vacuum, and we've also pressurized our detector chamber. As Vincent mentioned, we're able to stretch the mesh in a repeated process without flaw. We also take that mesh and we hook it up to voltage, and we see where the different sparks are occurring on this mesh, and then we make adjustments based off of where the sparks are. Additionally, we've assembled the field cage, which has our anode, our cathode, our PCB, and our meshes all together in a nice package that can go into the detector. As Ricky talked about, we've done focal length testing to ensure we're getting the best resolution photos, and we've created a camera lens housing to ensure that our detector is light tight in order to get great photos. And additionally, we've began assembling the detector onto our backpack frame. Our next steps in getting our detector running is to test the graphic user interface, assemble the detector, and then begin testing.
So the answer to this is to be able to take this assembly, put it on the back of a warfighter, allow them to use it so that they can use this with the graphics user interface, and send up information to the higher echelons of chain of command so that we can get the assets to handle these special nuclear material stockpiles.
A fast neutron detector that outputs a directional vector has boundless opportunity for future work, including its integration into battlefield surveillance technologies, augmented reality systems within the DoD, and usability and durability testings with different types of units for rugged environments within a battlefield context. We appreciate the support of the Defense Threat Reduction Agency, the Nuclear Science Engineering Research Center, and of course the Department of Physics and Nuclear Engineering in the completion and work on this project. Do you have any questions?
What would you consider to be, two questions, what would you consider to be the most sensitive part of the equipment for it to be deployed to the soldier? And second, what do you think is the most challenging to manufacture? Like what has the most likely to cause a failure within the design?
So right now, I think the most important focus for like future research would be take the camera assembly and shrink it down, because right now, as you can see, it's kind of on the top, kind of clunky. I wouldn't say it would survive a fall. Like the camera assembly itself would be damaged, and so that's like the most expensive portion of it, and also the most sensitive. Like, if it's going to be dropped and moved around a ton. So that would be the focus of being able to optimize that, make the CCD smaller and smaller, so we can actually be able to move it, drop it, and it still works.
As far as manufacturability goes and the reproduction in a mass context or in a repeatable context, the mesh and the ability to emplace the mesh, stretch it, and ensure its continuity is by far the most vulnerable for production and maintenance. If there are any sorts of disruptions on the mesh to include contaminants, dust, things like that, it'll need to be replaced. And over time, it may wear out due to the high voltage that it's held at. So designing the detector in a way that those meshes can be replaced continuously and repeatedly, as well as designing a system that can create them quickly, will be a difficult obstacle.
So once this is fielded to the warfighter, what kind of maintenance schedule do you anticipate it's going to be on? I mean, is it going to, I assume periodically you'll have to get it pressurized, refilled, and tested. Is that going to be a, every time it's deployed kind of thing? Is that going to be an annual inspection, those kind of things?
So every time we would use it, you'd want to optimize it, so it would have to be checked and maintenance every single time. Because really small flaws can end up causing, like there's a ton of them, it can cause a big loss of data. So optimally, we'd want to test it before we use it every single time.
And unfortunately, there's no way to put neutron sources or fission sources in a safe way next to the detector to ensure that it's operational. Instead, you can use, similar to most detectors, using a check source, an alpha source within it to calibrate and ensure that the detector is operational.
All right, thank you for your presentation. Let's give him one more round of applause. All right, our next presenter is Cadet Buendwa, and whenever you're ready, the floor is yours.
Okay, thank you. So today my presentation will be on infrared spectroscopy of regolith samples, specifically those that come from the moon. I'm Cadet Buendwa, space science major, and I'll be presenting for you. My advisor is Major Greener back there, and my counterpart advisor, University of Georgia, is Dr. Philip Stansel. So the agenda today will be a basic overview of the background, the experimental setup itself, what about the sample that I'm working with, sample 70215, as well as the purpose, the sample results, the theory that I used for this experiment, and the limitations and uncertainties, and finally the current obstacles and future suggestions for this experiment. So who is involved? So I actually worked at another University of Georgia in Athens, and I was working with Professor Philip C. Stansel, the department head of physics and astronomy, and the team was also included Dr. Thomas Orlando, and as well as Professor Giannis Abbott and another student named Adams Grace. In this experiment, we used 6 moon samples. I was looking at one sample 70215. I was using Fourier transform infrared spectroscopy to obtain my data, specifically the spectrum absorption and emission. And then from that, I was trying to see any inhomogeneity and composition change because it should change throughout the surface of the moon samples. So background, so why am I doing this? In order to identify the composition of moon samples produced from the FTIR, as well as to produce samples, in order to understand the composition of the moon samples from the FTIR in the lab, the goal as well is to create a database of mineral composition and to assist university in establishing a lab for future lunar samples and ask for return missions in the near future. So what is my part in all of this? My part is specifically to analyze the infrared spectral data and to conduct an in-depth literature research of this. How am I doing this? So I'm receiving data from the university itself, from the Nano FTIR, and the deliverable is a database of mineral composition spectra using a Lorentz oscillator fit for each sample composition. So for the sake of time, I will try to breeze over this, but if you have any questions, in-depth question, please ask at the end. So this is a general idea of the general setup of what was in the lab itself. And so before, this is FTIR, which is the data is collected by an interferometer over a large portion of an infrared region with each measurement. And so just a general idea of an FTIR is a light source is shot out, specifically from the broadband light source, and then they go through a beam splitter and then split into two. One is going to a primary mirror, and this one is a parabolic mirror, and then the second mirror is shot towards a moving mirror, and then these two lights are then shot back towards a beam splitter. They go back together, and then they redirected towards another mirror, which is then redirected towards the object which we're observing. Specifically, what was unique about this setup was the fact that they were using a nano FTIR as well as a scattering type scanning near field microscope in order to get better observation of the mineral sample. In addition, we use finite dipole models in order to get more precise idea of the infrared reading and measurements which we're looking from this setup. The resolution itself was about 100 nanometers. We're looking at about 2 to 4 micrometers of the object itself every time we're doing the measurements. The height itself of the mineral was 1 millimeter, and the area about 20 millimeters times 20 millimeters. The whole thing was conducted in room temperature, and again, there's 6 moon samples. And just reiterating, I'm looking at the inhomogeneity and composition change. So this is the sample itself. This is the bulk sample. We got a chip of this sample in this experiment. So this sample was actually just found lying on the lunar surface. And as you can see, there's like micrometer craters around it, which means that it actually went through tumbling around the moon before it's collected. There's also distinctly different textural regions on this moon, which pretty much mean that there was difference of cooling that occurred when it first was cooling from lava, which is further seen in observing their finer grained versus their coarser grained regions, which is just difference of cooling that occurred on the rock itself. And finally, this rock itself is yet to be correctly dated. There still need to do initial isotope ratio to better understand how old the rock itself is. So what's the purpose of me doing all of this? So the purpose is, on the grander scale of everything, is to gain a better understanding of mineral compositions of airless bodies, specifically also understand the effect of space weathering, as we saw from this moon sample. Just because we collect a regolith or a rock from an airless body does not mean that it has not gone through additional process or effect of the environment around it. such as micrometeorites, which are just impacts on the surface that produce gardening or soil, as well as melt, which is just changing properties from heat. So this is the results of our sample. So originally, I was looking at the difference between the literature and earlier research was the fact that they were looking at bulk samples. I was looking at a very small piece or scrap of the sample itself. And so looking at the bulk samples, on the left side, those are like what was identified to be present. So it was silica, oxygen, aluminum, iron. There's some instance of iron as well of nitrogen, sulfate. So so definitely what we're doing is, on my end, was looking at a smaller piece of that rock because it went through like tumbling, and also there's a difference throughout the surface. We expect the composition to change throughout the surface of this rock. And so the specific part that we're looking at, this is from the result that we got. So looking at using the FTIR samples and also mathematical calculations, plotting it and looking at the peaks of the regolith, and using a Loretz best fit, we could identify that there was about 47% enstatite in the sample that we're looking at, and about 30% olivine and A, which is just another variation of olivine and olivine C. And again, if you need specifics, we could talk about it later, but it was just different measurements of different composition of olivines. We also looked at it further from a different perspective of looking at phases versus wave number, amplitude versus wave number, contrary to using it photons versus reflectives. And this one, again, we're just doing the same thing. We're looking at the peaks of the amplitude and the phase to see what other chemical composition line up or match up to our given from the FTIR. And again, if you look at just like the peaks and how they align, for all of these, the actual moon sample itself, for the one on the left, it is the fainter black line in the background. And so just looking at some of the peaks that align to it, we can already assume that we can already see that what's present enstatite A and olivine C, as well as the MgO4 spinal, which is just another variation. We expect to be another variation of a spinal because it's shifted a little bit instead of matching exactly. And on the phase and wavelength, we do the same thing, and then we can identify that there is enstatite A, olivine B, and there is more on here, but that'll take more time to go over it exactly. So the theory itself that we looked at, so when I got information back from the lab, I got reflective and absorption. Mathematically, we can align this back to the real and imaginary parts in order to better use our data to plot the amplitude and wavelength and phase wavelength. Specifically, we were using classical dispersion theory to better mathematically solve what we were mathematically plot and understand what we're getting from the machine itself. So we use the complex dielectric function. The reason why we use this is in complex dielectric function, there's a real and imaginary part, which aligns with the data that we're getting, which is the absorption and reflectance. I just gave a general idea of the given mathematical we're working with is the square difference of longitudinal and transverse frequency nodes, the dampening, and the strength of the transverse optic vibration mode. So limitation of certainties in this project. Some limitation we had was there was always a chance of contamination. This rock was not sealed up as like the rocks we'll receive in the near future from NASA. There was also a chance of it being affected by solar wind effects, which could also play a part of the rocks changing composition. And also just limitation of working virtually. It was really hard to properly time and get everybody on the same page, especially with my cadet schedule. And also there's also always a possibility for mathematical error in data, which called for multiple people rechecking and looking at everybody's plots and mathematical computations, as well as the MATLAB data that was used to create my data results. So current obstacles and future suggestions for those who do take up this project. First, there was kind of a hard time doing connection between literature and experiment, since this is like a new terrain or a new place of working on. So I do suggest in the future there is like acquiring textbooks on more fundamentals, because Google was not always as helpful. The difficulties of working virtually, I would suggest that in the future that the cadets working on this do get at least one trip down to University of Georgia to actually see the lab and work in person with the team, as well as more cooperation with other student counterparts, the civilian counterparts. I did not always work with them efficiently, despite the fact that we were working conjointly on the same thing, and I was working off their work, they're working off my work. Next, I should start out more West Point sources sooner, and more importantly, delve into more studies of composition. We went down kind of a rabbit hole of math, which we did not need to go down as much. And secondly, we need further literature study to delve into samples with various chemical orders. And lastly, it's looking to space weathering, spectral data, and how the data changes from the effect of solar wind and micrometeorites. Micrometeoroids, my apologies. And this is my last slide, just acknowledgement, thanking Dr. Philip Stansel and Major Kramer for facilitating making this capable, as well as the PaNE staff and the Genie department. Thank you. Are there any questions? Yes, sir.
You mentioned that differential cooling can have effects on the grain structure on either side of the sample. Were you able to apply the process to either side of the sample, or was it just an individual sample from one side of the record? Were you able to compare the top versus the bottom?
So the funny thing is, I was not able to, but I know my counterpart was able to compare the top and the bottom, and they did see a difference. They did see a difference in not only the mineral composition, but also the variation of how, like, what was found, and also there was kind of a shift in data, which we kind of aligned to the rock being broadened, but also maybe just mathematical errors on our side as well. Yes, sir.
Curious, do you know if there's any interest in doing Raman spectroscopy to get a complementary vibrational mode information? To complement the IR.
Sorry, I missed the first part.
Raman spectroscopy, so the complementary vibrational mode technique.
Mm-hmm.
Do you know if there's any interest in doing, this to this project, adding the Raman aspect?
I do not know, but I think we are going to well, I won't be in the team next year, but there's an idea of shifting the way we are doing a few things, because the problem when using infrared spectroscopy was just it had a lot of math that we sometimes were not able to calculate, and that's why we went down a rabbit hole. And so there probably is going to be a shift of how we do measure and how we get our data to see if maybe we'll find something different. Any other questions? All right. Thank you for your attention.
All right, we'll now welcome back Cadet Willis for our next presenter. And whenever you're ready, go ahead.
All right. Thank you, ladies and gentlemen, for coming to my presentation. I'm going to be presenting on the detection of high latitude ionospheric plasma conditions leading to GPS scintillation. This is my second semester working on this project, and I'm being advised by Colonel Laux. So in plain language, what I am doing is I'm taking data from the Arctic Circle and trying to figure out when and where plasma structures within the aurora borealis move. So kind of this temporal and spatial inference about how these structures move in time and space. To explain all this, I'm going to be going through some background, then going through the research question, and then how I went about doing the correlation study to figure out how the aurora borealis moves. So operational background. Why is all this important to the Army for us to understand how the aurora and plasma moves inside the Arctic Circle? Well, first off, for the past 30 or so years, we've been having ice receding in the Arctic Circle, leaving more and more room inside the Arctic for trade routes. This has increased both civilian and military presence in the Arctic, making more people affected by the specific conditions within the Arctic Circle, such as increased plasma density within the ionosphere. Now, what that does, the added plasma in the ionosphere, is it adds basically this barrier in between GPS and satellites and receivers on the ground. So when GPS tries to penetrate through the ionosphere, it refracts and diffracts off of the plasma and electrons within the ionosphere, causing this phenomenon called scintillation, basically phase differences in the recorded signal on the ground. So basically what happens is there ends up being a disconnect between the actual location on the ground and the recorded location that is seen from the GPS, PNT errors. So having an understanding of the plasma and how it moves across space will help us understand how to better account for the GPS scintillation. The instrumentation that we're going to be using to conduct this correlation study that I'm about to do is collected from Poker Flats Incoherent Scatter Radar, PHISR for short. It's in Fairbanks, Alaska. It's an electronically steered array that basically juts out 5 beams of electromagnetic radiation. And based off of how much of that electromagnetic radiation is reflected back from the ionosphere, we can determine factors within the ionosphere such as plasma density and the altitude of the plasma. The incoherent scatter radar is targeted for the E region of the ionosphere, roughly 100 to 150 kilometers in range. However, it does have capabilities to look into the F region too, which is going up as far as 450 kilometers. The specific storm I'm going to be looking at for this correlation study is the geomagnetic storm of August of 2018. It was a coronal mass ejection, CME-produced event. That was rare for the time that it happened, considering that it was coming out of a solar minimum. The DST index was recorded to be about negative 171 nanoteslas. For reference, the threshold for something to be considered a geomagnetic storm is around negative 50 nanoteslas. So it's well below what is required to be a threshold of a geomagnetic storm. So on to my research question. I'm looking specifically how to spatially and temporally connect plasma structures shown in the separate 5 beams of the PHISR mode to each other, both spatially and temporally. This is going to help us understand the overarching science question of how does plasma within the ionosphere affect scintillation and PMT. So as you can see from this moving video right here, the aurora from the storm is generally moving from an east to west fashion, along with a diagram on the top showing the electron densities as it is moving through the ionosphere, showed by the color of the different plots within there, measuring the electron density. So essentially what I'm doing is I'm taking those separate beams within the top diagram and comparing them to each other. So this is the raw data that we're working for my correlation study. I'm only focusing on 2 of the 5 beams from PHISR, the center and east beam, denoted on the top. Breaking down the beams further are the 2 bottom diagrams, with both x-axis being in the time domain, along with the y-axis being the altitude of the electron density. So basically the color is showing where there's a higher density of electrons at that period of time. Think of it as basically getting cross-sections of those beams as it progresses over time. So the whole entire point of this correlation study is I'm looking at the center beam on the left and saying where does aspects of the center beam appear in the east beam. So to actually do this, we're going to be taking advantage of a theorem called the Wiener-Kinshine theorem. It's basically saying that when you have these 2 signal sets, if you overlay a section of the signal onto the other, and multiply like terms against each other and sum them all together, you'll get a value that represents how alike the two signals are. We can implement that with MATLAB using cross-correlation techniques, basically doing the same thing, both arrays, aligning two arrays on top of each other, multiplying like terms together, and that value being how alike the two signals are. We do have to normalize the cross-correlation afterwards in order to make sure that we're kind of comparing apples with apples, and it also produces an R² value for us to actually show quantitatively how alike the two signals are. So the correlation concept is we're basically going to be doing this cross-correlation technique, iteratively comparing small sections of the center beam to the entirety of the east beam over and over and over again to try to draw out this displacement. So to break that down a little bit more, I've kind of zoomed in on a specific section of both the center beam and the east beam, specifically looking at that structure in the center beam that's much more red than everything else. So what I'm talking about with taking a small section of the center beam is literally just taking a box of it, showing that box in red, and cross-correlating that to the entirety of the east beam. Doing the cross-correlation technique shows where in the east beam is the area that's most similar to that box in the center beam, shown by the second box in the east beam. Those are basically the two areas that are most similar to each other within the two beams. I show where they are compared to each other by using a vector in the bottom left-hand corner of the center beam. This is basically showing at the base where the bottom left-hand corner of the subsection in the center beam is, and where we are showing it to be moved in the east beam, going to the top, to the bottom left corner of the head in the east beam. So we're going to be doing that iteratively every single possible subsection of the center beam to get all of them, to get every possible correlation, except now we're going to omit weak R² values. So basically correlations that are not deemed significant. For the purpose of the study for this storm, I've put that at 0.4 as an R² value. We're also going to omit the red boxes just because that's general clutter in the image. Our final result is what's seen here. You can generally see the displacement vectors going up and to the left from the center beam to the east beam. What that is saying is that the plasma density is showing up earlier in the east beam and also higher in the east beam with comparison to the center beam. So generally, you're seeing it go from east to west. Also, what we saw in the all-sky imager at the very beginning. And it also has the added information that it's getting lowered in altitude as we're going through. So, we are also able to do some velocities from this cross-correlation, showing that generally it's between its components, southeast and zenith, or altitude components, are what's shown up here, again, generally going in a westward motion. Putting that out of the time and altitude space into all three dimensions of space, southeast, zenith, I'm going to be showing a little bit more empirically what's going on, trying to convince you guys that the cross-correlation is correct. We have the two beams jutting out, with the east beam being the line that's a little bit lower, the center beam being the one that's a little bit higher. At a very specific point in time, as shown up top, when I change the slide, it's going to be incrementing that time interval forward by 15 seconds. And what we expect is that the plasma densities from the east beam to the center beams to follow the displacement vectors that are the red arrows in the center. So when I flip it over right now, you should see the red dots move from the east beam to the center beam as predicted by the arrows, which is generally what we see for this segment in time. So I'll go ahead and repeat that again. We're seeing them in the east beam, and then as the prediction says, it should be going downwards generally and towards the center beam, showing the motion in time and space of the plasma densities. So the results right now, because we are only comparing two beams, we only have two spatial dimensions of inference, the one going along the route of the two beams and the altitude. We also have the temporal dimension of inference, where we're seeing when it shows up along with where. We're also showing the altitude displacement, which is something that the all-sky camera down here could not show because it doesn't have any depth to it. So we're getting a little bit more future information there. Additionally, we have, as far as future studies, we plan to implement more beams in future semesters in order to increase the amount of spatial dimensions you can make inferences from 2 spatial dimensions to 3. We also plan to cross-verify more with the all-sky imager down here to make sure that everything's kind of lining up with the velocities of the plasma densities between the two forms of imagery, and possibly going to quantify the gradient drift instability of the plasma structures as they move. So again, just showing that all-sky imager, they're both showing generally the same thing, going east to west. Same thing with our correlation analysis up top. Generally lining up. We want to get a little bit more rigor in that in the future, but it looks like it's going in the right direction. So, and why does this matter for us? Going back to the idea of understanding the underlying physics behind mechanisms that affect the military, such as scintillation. Having understanding of when and where plasma shows up will make it easier to actually characterize how plasma densities affect scintillation, and may in the future affect how we can mitigate the effects of scintillation in precision navigation and timing. Additionally, we have other effects such as the SpaceX launches a few months ago that ultimately failed, and they lost 40 satellites because they did not properly account for ionospheric conditions, which this project is aiming to have a better understanding of. I would thank Colonel Laux for advising me in all this, and pending any questions, this concludes my brief. Yes, sir.
I got one for you. So you mentioned that you're taking kind of your data set and then comparing it to the eye in the sky, and that allows you to correlate your east-west data. But is there anything out there that allows you to confirm the zenith portion of your data, or realistically, are you kind of the first one to kind of provide a data set on that?
So you can make inference about the altitude based off of the color of the aurora, because it precipitates differently at different altitudes. So that's a rough estimate. I imagine there's also different techniques using different satellites, different ISR platforms at different areas to get the depth. This is the first time we're attempting to get altitude inferences from a single radar node.
Thank you.
Yes, sir?
How much do you think the time of the year would play into this?
So, especially in Arctic regions in the summer where there is no night, it'd be much more difficult to do this, mainly because the plasma coming from the sun kind of drowns out the plasma coming from CME events, so it's just generally loud all over, and it'd be much more difficult to actually get any correlation from it. But mainly in the night when there isn't too much background plasma running around in the ionosphere, it's much easier to show this. Thank you for your time. Oh, one more. Yes, sir? Oh, wow.
All right, so our next presenters are Cadets Osborne and Espenshade. Whenever you're ready.
Ladies and gentlemen, thank you for coming out today. My name is Cadet Anastasia Osborne, and I'm joined with Cadet Espenshade. And today we're going to talk to you about our research this semester, which is correlating solar wind variations to the timing of field-aligned current flow. All right, so I'm sure you guys have heard a lot about space weather today, but just as a little bit of a background and a refresher, The solar weather, or the space weather that we're primarily going to cover that impacts our topic, sort of describes the variations in the space environment between the sun and the Earth. In particular, space weather describes the phenomena that impact systems and technologies in orbit on Earth. Space weather can describe anything from the surface of the Earth to the surface of the sun. As the space weather storm leaves the sun, it passes through the corona and into the solar winds. When it reaches Earth, it energizes Earth's magnetosphere and accelerates electrons and protons down through Earth's magnetic field lines, where they collide with the atmosphere and the ionosphere, particularly at high latitudes. Each component of space weather impacts the Earth a little bit differently. Something that I think it's important to note up front is that this research is actually a continuation of a research project from the class of 2020, Cadet Anna Maria Deer, now Lieutenant Deer. Her research was very influential and allowed us to start this project, and one of the primary goals is to better understand this physics and pass it to more generations or new classes for being able to work with sort of this field-aligned current understanding.
So building on what Cadet Osborne just said, the significance of space weather, especially particularly relating to the Army. So we're working on forecasting and signal detecting, hopefully for the future, being able to work on communications with radios and make sure that space weather doesn't disturb too much, or being able to break that in the future. And the focus for our research is determining if the currents caused by magnetic merging or convection of plasma in the magnetosphere following night-side reconnection. And Cadet Osborne has the graphs for that.
Okay, so now I'll move you more towards our actual conclusions or how we performed this data, or this sort of correlation. First, I wanted to acknowledge where we actually got this data from. The solar wind data was downloaded from NASA's OmniWeb, which is an open website. You can download it with different indexes. The optical imagery data was provided by Dr. Don Hampton at the Poker Flat Research Center. And the data that we particularly used, or ones that we picked out of like the date range, we wanted to have diffuse aurora, have that 630 nanometer, that red line emission, and a KP index of 2 to 2+ to have like somewhat of a quiet, nothing too crazy, but just to have like good data that wouldn't impact our cross correlation too much. So as you can see here, we have 4 different plots there that compare magnetic flux density to magnetic activity. Specifically, the one up top can give us more of the IMF component. Magnetic flux density to the symmetric disturbance for the horizontal components, magnetic flux density and auroral electrodets, and the meridian spectrograph measurements of auroral intensity at the bottom. And sort of that squish one is a little bit of the keogram. You'll see a better one about 2 slides from now. So next, we have what we produced from those 4 things. To the left, we have that spectrograph, and to the right is what I really want to draw your attention to, sort of this cross-correlation. So this cross-correlation stem plot is a function applied to the magnetic activity and the auroral intensity data that we got. For this particular, it shows October 31st, 2015, had a KP index of about 2+, which was within the range of what we wanted to look at, a lag of around like negative 2.08 hours, which was around the same as the other data that we got, an RMS speed of 414 kilometers per second, and time to the magnetopause around 51.4 minutes. So we took this data from what we did for this semester and compared it to some of the findings from the previous semester. Now, what's really important to note is the cross-correlation from the other semesters, or the previous research does support this about 1.9 to 2.08 lag time from the cross-correlation data, and we found that that was pretty consistent, which was good because that's what we were expecting to find from the data. Specifically, when you're looking at this, the magnetic field component from 2 to 1800 on 3 February, and just the different like meridian spectrograph measurements of auroral intensity. Not pictured is the cross-correlation that was performed between the 2 of them. An important conclusion that we wanted to draw from this does support some of the original work. So assuming tail reconnection happens 1 hour after the southward IMF reaches the magnetopause, the 2-hour lag time that we found between solar wind measurements near the L1 Lagrange point and terrestrial auroral detection suggests the night side reconnection drives the field-aligned current movements. So now moving into future work, or sort of a recap of what we have done throughout the semester. Primarily, this work involves taking the MATLAB code that we were given, changing it from 2019 to a 2021B. Something that I had to work through was reading someone else's MATLAB and being able to understand what it does, change it for our specific purposes, and something that I want to pass along to future researchers is the ability to maybe have coding or like comments that are a little bit better. I was even thinking about doing a video of walking through and specifically coding what each one does, because you never know what someone is coming into this research level at. Like if they're really good at MATLAB, if they're going to be where I was, somewhat familiar but not entirely sure how to do these more advanced functions. Something that I think could also help this research would be incorporating more dates in the data examination to really confirm that lag time, refining the figures for more ease of interpretation of being able to present them. Something that could also be interesting is not only incorporating data with a KP index of 2 to 2+, but something with maybe a more dynamic or a larger space weather event to see if this lag time is still the same or if we get any issues with the data. But I thought it was important for this to stick with kind of our baseline. And as Cadet Willis mentioned, some of the real applications or why we do research like this is to make sure that we understand the basic physics behind why things like satellite scintillation occurs, and maybe in the future being able to take this research and use it as the basis for different research events, maybe bridging field-aligned current flow with understanding satellite scintillation and being able to mitigate for it a little bit more. Pending any questions, ladies and gentlemen, this concludes our brief. Questions?
All right. Thank you. All right, so our next presenter is Cadet Harris, and go ahead whenever you're ready.
Yep. Ladies and gentlemen, my name is Cadet Harris, and this is the effect of density enhancements on radio wave propagation in the upper region of the ionosphere. So we're going to go over our problem statement, end state, a little bit of motivation, how we solved our model equations, and then some of the effects of the radio wave propagation in the ionosphere. So the problem that we're looking at is that as GPS signals pass through the ionosphere, the receivers on the ground are getting inaccurate position data. My hypothesis was that the optical densities of the ionosphere were causing scintillation effects of the radio waves as they're passing through. So as most of us, I guess, are familiar, as a wave of light passes through a medium, the wavelength changes based off of the permittivity of that medium. So I was thinking, okay, maybe the optical densities change, and I wanted to figure out a way to model and involve those optical densities. So I looked for a physical system to inform my initial value problem, and I think I found polar cap patches as the most likely cause of this plasma organization. So basically, as high and low density plasma sit adjacent to one another, if there exists a favorable gradient condition, then the plasma is unstable. Given a perturbation of that medium, the plasma becomes organized and locked into place using the E and the B fields. So this basically informed our initial value problem and kind of some of the physical evolution of the system. So that's swarm data from the poker flat, I believe, and that's basically showing kind of what Cadet Wills was showing with the day side and night side plasma densities and the lower and higher density plasmas. So the selection of our model, there's a range of models to simulate plasma in fusion reactors and the ionosphere. The magnetohydrodynamic model is the simplest model. It models it as a single electrically conducting fluid. It's pretty computationally feasible, but it doesn't really capture the charge separation effects that we're looking for. The two-fluid plasma model is, again, computationally feasible, takes advantage of Navier-Stokes equations, and it captures the two-fluid effects, and it's scalable, so we can incorporate neutral atoms for stuff in the FE region. Finally, the Maxwell-Vlasov model. It's the most physically accurate because it's a derivative of the Boltzmann transport equation and tracks individual particles, but it's just not feasible for our computational domain. So this is the model that we use. There we go. Cool. So this is the two-fluid plasma model. Up here we have the conservation of mass, momentum, density, and energy. So we're operating on the assumption that no mass is leaving our system, and that momentum and energy have some source term associated with it that changes based off the electric and magnetic field. And that's basically how we coupled our Maxwell's equations down here to our fluid equations, the Navier-Stokes equations. When we solved it, we preserved our divergence constraints associated with Gauss's law. And these are our permanent variables. So this is what we're solving for. Finally, this is a determined system of equation. We have 5 equations and 5 unknowns. So you can use some PDE solvers to solve these and just come up with the evolution of the fluid. So like I said, the polar cap patches informed our initial value problem. When we have that favorable gradient condition, the E and the B field, and a density gradient pointing from plasma of lower density to higher density, we have something called a Riemann problem, which is a specific value problem, or which is a value problem with specific initial data separated by a discontinuity. So there's several different ways to resolve this, like contact discontinuity, and evolve the system. Because our equations appear in balance law form, we can use a conserved equation, or a conservative equation to solve for that. So here, Q is our conservative variables, F is our flux variables, and S is our source terms. So the conserved variables are mass, momentum, density, and energy, and then our flux terms, the numerical flux between the cells in our computational domain. And then they're coupled explicitly using the source terms and I'll discuss it later, but the eigenvalues of the source term are small. So this is the basis, the mathematical basis for a row solver. So as you can see, I rewrote the conservative form. To find the flux, we used this equation, which is half of the left and right going fluxes for the initial data, minus 1/2 of the sum of the wave strengths, eigenvalues, and eigenvectors. So this piece right here was done by Rowe, and he used a parameter vector and solved for the eigenvalues or eigenvectors and eigenvalues of that source Jacobian. And that's done in the usual way, where you take the determinant minus the identity matrix times the eigenvalue. And these are the wave strengths. So in various initial condition problem, or in various initial value problems in fluid dynamics, there's different types of wave strengths associated with rarefaction, shock wave, and contact discontinuity movement, and that is how you resolve them. Moving on to the source terms, one thing to note is that we set the source terms to 0 and solve for just the advection terms for our flux here for the conservative form. So moving on to the source terms, we did the opposite. We set our flux terms equal to 0 and cast it as a system of ODEs. When I solved for the eigenvalues, so I wanted to classify these because I wanted to know which numerical method to use to evolve the terms. And I found that the eigenvalue is something physical. It was the electron cyclotron resonance frequency. Or actually, it's the charge species cyclotron resonance frequency. So these numerical equations are stiff because the electron is moving against the ions, and that is a much slower manifold than just the charged particles. Yep, and that's basically described here, that the eigenvalues source Jacobian indicate differences in speeds and species. So moving on, in order to couple the Maxwell's equations, I solved them using a finite difference method and mapped it against the cell densities. And I found that the electric field was very close to the charge or the current densities in the plasma. And the magnetic field, I think this indicates some numerical difficulties with our method. Either that the finite difference method was not mapped perfectly onto the finite volume method, or that some divergence constraint was not preserved. Oh, and one thing to note is we didn't use gauge conditions to solve for it. I know it's very typical when solving Maxwell's equations to use gauge conditions. Because I consider an infinite computational domain, I use absorbing boundary conditions and explicitly incorporate the source terms every node. So for the radio wave propagation, I used a method of acoustics outlined in a Levesque paper, basically here, and it's solved for the eigenvalues. At the vacuum limit, this is immediately recognized as the speed of light. And then I modeled that radio wave propagation without hardwired source term, or without source terms hardwired to the nodes, and rather using a basis function of just a plane wave propagating from the satellite through the medium. So in order to solve for the wave numbers, because that's what I connected to for the position, like the deformation of the wave in position, I used the permeability and the permittivity of the medium. I assumed that the permeability was vacuum permeability based off some literature. And then I found that the permittivity is dependent on the plasma frequency, which depends on the density of that medium, which is kind of why we're solving for the optical densities of the material as the radio wave passed through it. And then, just recognizing physics 1 equation, the wave number is calculated with the eigenvalues and the frequency. And that is the wavelength calculated using the eigenvalues, which is the speed of the wave and the medium. So here's what we found based off of our Riemann solver. So the wave number of a GPS signal in a vacuum is 33.01. And we found some very close values based off our normalization, or unnormalizing our constants. However, some of our numerical difficulties and some things to consider is that several initial conditions yield unphysical results. As you can see, the wave number in shock tubes and sod shock problems fall below the wave value of a wave number in a vacuum, which could mean that the speed of light or conservation of energy is being violated. So that's something to consider and continue working through in the model. And what I was hoping to validate and what I hope to validate as I continue to couple the electromagnetic waves is that the wavelength is changing, which is essentially removing some of the information modulated on that group, and we're losing data. This concludes my brief. Are there any questions? So for our computational domain, we separate into 400 cells. For this is just a way to visualize the initial value problem. So the plasma structure in the ionosphere can be kilometers, and that's why we modeled it as an infinite computational domain and didn't use those gauge conditions. But this is just to be able to discuss basically what we're doing. These are two differing densities adjacent to one another.
So if it's kilometer size, and you're trying to propagate through it,
Yes.
Where does the scintillation come from?
So as the radio wave, so this is in one dimension. Something to consider is this is in one dimension. So as the radio wave propagates through that medium, the plasma is being organized in these large columns. So as it propagates through the varying optical densities, the wavelength is changing as it goes in and out, and that changes the speed of the wave. So I have two hypotheses on where the information is actually lost. One of them is the change in the wavelength as it goes through the optical densities, cutting off information of the phase, or of the modulated information in that group. And the other one is the way that GPS works, the triangulation of the different waves. It knows its position and it knows the speed at which it expects the wave to pass through that. So if you're going through different optical densities, the speeds at which those radio waves are passing through them are going to give you a wrong triangulation. And even with that forced satellite that we typically use for error correction, is also going to be affected by these large plasma structures. Does that answer your question?
Yes, so how do you think, if those densities are changing, do you think they're changing randomly?
So they're changing based off of the initial conditions of our problem and the presence of the E and the B field. So when we solve our problem, so I chose to validate the approximate Riemann solver, I chose initial conditions that have already been validated in previous work, because those are proved to be physical and can be used in this approximate, or in these solvers. With the two fluid plasma equations, we couple them with the E and the B field using Maxwell's equations. And that changes how these are organized. Okay. Any questions? Yes, sir.
Go to the slide that had the eigenvalues on it. I think it was, yeah, that one.
Yes, sir.
Why does the speed of sound matter?
Oh, so this isn't the speed of, so this is the electron ion speed of sound. So these are, I wish I would put these up there, but this is the ion electron speed of sound. So this is how fast the information propagates across the cells.
So it's not a shockwave kind of speed.
That's what it is. So these are modeled as like current densities because of the fact they're electrons and ions, and they move and they propagate at the speed at their speed of sound in the fluid.
Okay. My second question.
Yes, sir.
That helps. So this is, how dense is the plasma? I know nothing about ionospheric physics, but from my limited understanding on optical interference with plasmas, it is highly nonlinear. So is the plasma not dense enough that you have to worry about higher order nonlinear terms in the optics? I see the permittivity is only the first order. You use the permeability as the vacuum, but the permittivity is first order.
Yes, sir.
Which leads me to believe that we're not examining effects of nonlinear optics.
Yes, sir. I did not investigate the effects of nonlinear optics. What I found was that the plasma frequency affects the permittivity of the plasma as the radio wave propagates through it. Based off of the frequency of that wave, I did not consider higher order terms or nonlinear terms in that calculation.
How hard would it be to incorporate them? Did you have that term as a separate function that you can just change the function and it'll change your code, or do you got to rechange every line in your code?
This is scalable, so I have the function such that we can just include higher order terms onto this. But it takes further research. I need to understand more about the nonlinearity and additional terms.
All right. Thank you for the presentation. It's going to be another
You don't know that. Have you seen this presentation?
All right. Our final presenters for the morning, Cadets Zhang, Hu, Flowers, and Godsville. Whenever you guys are ready, the floor is yours.
Thank you, sir. Good morning, ladies and gentlemen. Today we'll be talking about chip-scale atomic clocks, gravitational time dilation, and be using CSACs as a platform for testing and characterizing high-altitude balloon flights. For our agenda today, we're going to talk a little bit of an overview of what a CSAC is, some of the errors associated with that, GTD as a whole, some of the stability issues, design, data, and future work on characterizing the clocks.
First, to introduce how a CSAC can be compared to a regular clock. First, in a regular clock, you have an oscillator. That could be a pendulum. In a grandfather clock, that could be a quartz oscillator and a wristwatch. In our experiment, our oscillator is the CSAC itself. And then you'll need something, a counter, to accumulate those oscillator patterns. And in a regular clock, that may be a mechanism. In our experiment, we're using a frequency counter. And lastly, you have your icon. That may be the watch face or the head of the clock, representing the time that has been accumulated. In our experiment, we're using data frequency software to represent that. And rudimentary understanding of how a CSAC operates is cesium electrons can transition between states, and an infrared laser is used to read off the difference between those states, and that is used to help guide the crystal oscillator that exists in the CSAC, and then is reported as time.
Alrighty, when dealing with timekeeping devices, we're faced with three primary regions of error. There will be phase error, frequency error, and predictability error. Phase error occurs when two clocks are essentially out of sync with each other, and they'll accumulate and further propagate differences in frequency. Frequency error is when the difference in frequency between the two sets of oscillators means that they will further drift apart from each other. And predictability error is essentially when dealing with chip-scale atomic clocks, it's a stability error of sorts. We use Allen deviation to further characterize and identify specific chip-scale atomic clocks because when dealing with these, because they're atomic-based, they'll have their own characteristics associated with them.
Allen deviation is the international standard that is used to characterize frequency stability. It is similar to, but not the same as, standard deviation. It uses the previous two terms in the series to compare to the average. This can be changed through frequency drift, aging error, and temperature changes. As you can see, there's two different equations used for time difference data and frequency data.
So in order to learn a little bit more about how our CSACs behave in the atmosphere, one thing that we do is we put them on high altitude balloon launches. And so our goal that we've had since we started working with CSACs is to experimentally measure gravitational time dilation with them on a balloon launch. And so what that is, basically it comes from Einstein's theory of general relativity, which is about space and time, and basically says they're one and the same, and that the closer you get to a large massive object, the slower time moves. So you can see in equation 3, this is the gravitational time dilation at Earth's surface. So basically, to put it simply, like that right-hand term, that factor in the denominator is essentially like the Earth affecting time and showing that time dilation. The equation we're working with is equation 4, which shows the fractional time dilation between two different clocks at different altitudes. Next slide. And so from that equation, the force of gravity, we run into some challenges because as we go up on our balloon launch, that force is changing, getting weaker as you go up. So in this top graph, we have the altitude as a function of time, and then in this bottom graph right here, we have gravity, the force of gravity as a function of altitude. So we came up with this numerical integration method, where basically we integrate on our graph here, and then we can account for the changing force of gravity to account for that. So these high altitude balloon launches are good because it goes up fast and there's a large enough altitude difference to be able to see gravitational time dilation with our CSACs while they're still stable and accurate out to the 10th or to the 9th decimal place. But we haven't been able to find that yet. Our theoretical models show it would be around 20 nanoseconds of difference in time. But we've run into some errors from different things, which we'll talk about. But it has been good because it's caused us to challenge us to learn more about how they behave in the atmosphere and learn more about the CSEC stability.
First, a comment on just the elephant in the room. I believe that there might have been some importation issues. It may look like that, but it's actually a length contraction, a relativistic theory, which it's actually a feature of our presentation. So that's the reason for some of the formatting issues you might see. But going into some of the experimental basis on the GTD, so as Aaron was saying, so some of the conditions that we're experiencing under the high altitude balloon is we're having to do this under perfect conditions. So that assumes things like a constant temperature, low pressure, no pressure changes, as well as short duration high altitude balloon flights, as well as maintaining an atomic clock between the quartz oscillator and the clock. But for some of the theoretical examples, so Allen deviation as a whole across short interval periods, your standard deviation in time might be enough for what we theoretically calculated these balloon flight time dilations in order to disprove the null, as it were, in terms of numerous amounts of samples and showing gravitational time dilation.
Alrighty, so dealing with design, we work primarily within 3 different environments: our laboratory, pre-launch, and launch environment. Now, why do we do this? We do this because we want to ensure that we are as accurate and as precise as possible in our measurements, whilst also being mobile at the same time to allow for that high altitude balloon launch capabilities. Just a rough overview of the steps. We power on and lock each of the chip scale atomic clocks. We ensure that our reference and our experimental CSEC are connected so that we can get an identical initial phase difference. What this allows us to do is any data that's collected during the flight, we can ensure that it's not an error on the front end of our setup. Going through the laboratory environment, pretty simple. Everything's connected to power. Everything's being measured. Pre-launch, what we do is we have our CSEC-B, which is our experimental CSEC that goes up in a high-altitude balloon. Is connected to a lithium polymer battery. The rest of them are connected up to their respective battery tanks. And then within our launch environment, we have our styrofoam enclosure, which includes our atomic pi recording device, our SparkFun Redboard, which records environment variables, our CSAC, and then we have the other CSACs connected as per the pre-launch environment.
So diving into our launch that just happened last weekend on 23rd of April. So in a conclusion, essentially the data we required after the launch was unusable due to one of these unknown errors that occurred probably during flight, losing its atomic lock. Previously, last year, we know that we can acquire data on the back end that is within parameters. However, for this data, it's unusable after the post-launch. However, we were able to get the phase difference data as well as the Allen deviation pre and post-launch. For some of our alternate data analysis that we've looked at in the past, just to go over this in overview really quickly, we've assumed linearity for some parts when we want to measure data prior to and assume afterwards, where we can't measure data after the launch precisely. And then we've also looked at some 2-sample variants similar to Allen deviation, but more in the frequency Allen deviation example.
Alrighty, so dealing with methodology. So these are essentially the steps that we take to deal with the technicalities with the electronics of being able to detect gravitational time dilation. Going through the steps kind of rudimentary, we have our atomic pi, which is labeled in figure 19 on the left there. It's essentially the single board computer that takes all the data, records it, and stores it. The CSAC is labeled in figure 20 right there in the middle, and then figure 21 is our weather shield that gathers environmental variable data. Each one of these is connected to the atomic pi via a serial port and is listened to on a specific directory. The storage device will then format for data write, and we ensure that our data is saved in packets. Because our high altitude balloon operation is risky in the sense that power loss can occur at any time, there's a multitude of other factors that kind of go into dealing with electronics. We want to ensure that none of our data is kind of lost while we're launching. And then highlighted in yellow here is just a small snippet of all the data that we get and we're able to record and store.
So from the first of our 2 balloon launches this semester, we were able to get some temperature data. So as we know, the change in temperature doesn't do the same thing all the way up through the atmosphere. It decreases, then increases, goes back and forth. And so our data we recorded paralleled that, except that it was just a little bit hotter because we were operating our payload in a styrofoam payload, which insulated, made some heat. So what we did is we were able to work in the chemistry lab and use our oven to mimic and create those same like temperatures and see how the CSACs operate at those same temperatures that they were at on the balloon flight. So
here are some of the Allen deviation graphs and plots. On the top right, we have our experimental CSAC tested over 6 to 7 days in a period, multiple times. And as you can see, there's repeatability with that Allen deviation up into a point of around 5 to 6,000 averaging time of seconds. And on the left, top left, we have the difference in temperature data as we use the oven. And as you can see, it takes a lot less time, averaging time for it to become unpredictable and lose stability.
So for our next steps, first off, we need to measure CSACs while they're in the air, either through a light oscilloscope or frequency counter. And also we need to do further testing of the CSACs at all temperatures and environments experienced within a high altitude balloon. Obviously our payload is styrofoam, so in actuality it might change depending on what kind of environment we are in. But we also need to experiment with different temperatures, pressures, even impact rates, as well as obtain GPS and measure for bias rate for future projects. That concludes our brief. Are there any questions? And yeah.
Okay, I'm just curious. Why is it important to test at higher temperatures at about like 30 Celsius? Because wouldn't it get cold as it's going up on the balloon flight?
So yes, so that was part of our what happened in our payload. So it's in the styrofoam enclosure, so it's insulated. The CSAC itself is going to be heated up, and then also the battery, as well as like our other devices. So the atomic pi, it's all heating up inside that enclosure. If we had a temperature variable enclosure where we could monitor the temperature, it might not be necessary, and we can maintain 25 degrees Celsius. But as of currently, we don't have that.
So you'll have to forgive me, I'm not super familiar with Einstein's theories, but is there a reason for launching the balloon to measure time dilation versus just putting a clock at the bottom of Bartlett and on the roof of Bartlett and waiting a long time?
Yeah, so one of the things with that's unique for this high altitude balloon, which is good for our this project, is it acquires a lot of altitude really quickly. Because if you're putting it down here and at Bartlett, it's going to be a long time before you experience that much time dilation. So it's about every kilometer is about 9 nanoseconds time difference in a day, so 24 hours. But if you get up to like 120,000 feet or like 30,000 meters, you're going to be getting like close to 30 or 40 across a 2 to 3 hour interval. So you could get a lot higher. And then that also, with that short time interval, you can be more sure of your stability.
Any chance of interdisciplinary work with sphere?
Yes, sir. I think for that, though, we need to do more characterization of the CSACs themselves, because during this flight, for some reason, it lost its lock. So basically, the oscillator wasn't like, the course oscillator was essentially running by itself, not really locked onto the cesium. So we need to test why that happened. If it was like a jolt that happened, then we probably wouldn't be able to get any usable data.
You guys have a hypothesis as to why it happened?
Or? You can lose atomic clock in a variety of ways. If it goes out of its operating temperatures, so like underneath a certain temperature or over a certain temperature, it could do that. If it has a jolt, I'm guessing it was most likely a jolt. Dr. K?
Go back to slide 5. One more. 4. You went through this too quickly. I want to see your structure. Okay, so it's cesium levels. How big? Oh, there, perfect. The coffee bean. I was curious to know how big this was and how you're actually working with the cesium. And I'm assuming there's built-in diodes. Are you? Is this off the shelf? You
So
guys just plug and
yes,
play?
sir. So this is from yeah. You want to answer that? So
Yeah, so they're from a company that manufactures them, Micro Semi, and so we just kind of were able to order them and then start plugging and play, kind of like you said.
Okay. What is the resolution on time that you have? How many decimal places can you get accurately?
yes, sir. So the specifications themselves say about within 5 nanoseconds is what you're getting. The actual output itself is a 10 megahertz signal, and then we measure. What we're actually doing for measurement is the phase difference comparing between one CSEC and another one, and that one just depends on how good our oscilloscope or frequency counter is. And usually it's within the oscilloscope is, I believe, 2 nanoseconds is the shortest you can get in with, and the time difference counter is within a range about the nanosecond to picosecond range.
Final question. I guess you have to retrieve this data from the thing after the balloon lands. You're not doing this remotely.
So there were originally plans to be able to do it remotely. The only issue currently is to be able to get that data drawn while it's in flight. We need to utilize, if you want to go to the future work slide, is being able to use picometer sorts. Just because our time interval counter itself, they're pretty big devices. They rely on pretty heavy electronics. Being able to take that data and store it locally itself would be just a huge amount of data. If we want to be able to parse the data and then store it locally, again, a huge amount of processing power that's associated with that.
How much data are you talking?
Sir?
How much data are you talking?
Well, what we originally had is we were using an oscilloscope within our lab. Being able to take a screenshot, essentially, or not necessarily a screenshot, but a snapshot in time of the data itself. I don't know the exact size of the data that it was, but it was a large amount of data. I think spanning only over a couple minutes itself was very hard to go through. So that's why we're relying solely right now upon the 1 pulse per second, and then just deriving that time difference between the two different chip scale atomic clocks.
So are there any of these, any examples of these being flown on orbit? And if so, is any of the data available that you could look to maybe project out effects while on orbit?
I'm not sure about on orbit, man, but the contact group, I believe, or Compass group in University of Colorado, what they're doing is essentially the same. They're doing ground testing of these CSECs when they're supposed to be in orbit. We're doing it more in the high altitude balloon level, but they're doing ground testing.
I guess I'm not totally sure on the different sizes of atomic clocks, because like there's big atomic clocks like that we've had originally, and then like these are, you know, obviously the newer and smaller one, and still kind of trying to figure out, I guess, how they work.
All right, let's give them another round of applause. All right, so ladies and gentlemen, thank you for joining us to hear a little bit about what extraordinary research is being done by our talented cadets here in the Department of Physics and Nuclear Engineering. This does conclude the presentations for the morning. Thank you.
Touchdown! Playing Frisbee, breaking my face.